Okay, this is lecture 6. This will be part 1. The total topic is compound stoichiometry and introduction of the mole, Avogadro's number, and then that will be this lecture. And then part 2 will be the path from percent composition all the way to molecular formula. So this is part 1 of 2. And going to the slides. Where are we here? Okay, so these slides is currently sitting in module 5, but the lecturer's slides are 05_compound stoichiometry. And stoichiometry is basically accounting in chemistry. It's keeping track of the matter, of the atoms, ions, compounds, depending on what it is you're keeping track of. And we're able to do stoichiometry because of the mass laws. So the fact that matter is not created or destroyed, the first mass law, therefore, whatever we have at the start of a reaction, we will have at the end. And so we can say a certain amount of product is made per reactant. We can say a certain amount of atom is consumed. Because we know what we start with, we will know what we end up with. It's just rearranged. And the other mass law, and you will see this when we go to empirical formula, the second part of the lecture, this will really come into play, that the atoms in the compounds are always found in fixed ratios, and they are always in whole number ratios. So we're using that in an empirical formula to be able to come up with the formula. So we don't use decimals in chemical formulas. So right, so just reviewing Dalton's atomic theory, which we still use today, that of course matter is composed of atoms, and now since then we know that it's actually atom is not the smallest number or smallest particle. We actually go electrons, neutrons, protons, and then even smaller particles that make up those. But at the time, Dalton's time, the atom was the smallest particle. But all atoms of a given element are identical, so all helium atoms will be identical to all helium atoms. All aluminum atoms will be identical to all aluminum atoms. And by the same token, all molecules, we can now extract from this and say all molecules are the same if it's identical molecule. All water molecules will behave like every other water molecule. And of course, atoms are not created or destroyed. This goes back to the first mass law. They are rearranged, and the whole number ratios, which we are going to use, and you're going to see how important that is. So this is stoichiometry. Stoichiometry is the ratio of atoms used with each other, of atoms, molecules, ions, elements used in a reaction. It's the ratio of each. And we can talk about these ratios in the same way we talked about unit definitions. This is, in a sense, a definition. So I will go to the whiteboard to look at our barium phosphate here. And we're going to break this down a number of different ways to show you how we can use stoichiometry. I'm very excited. My new pens came in. Thank you, Amazon. They won't dry up quickly, and I have all kinds of colors. I like color. All right. So barium phosphate. And I'm going to cheat and look at the slide because it's already been a long day. 3PO4 2. Now, notice I had to put parentheses around my phosphate ion because I have 2 of them. So your subscript around a polyatomic, you have to put parentheses because you're saying it's 2 of everything inside there. And by looking at this, what can you say about the charges on these? Remember, ionic compounds are matched, paired by the charge. Well, if you remember the crisscross method, we did this to get the charges, which means this 2 started up here and this 3 started up here. So the barium is a 2+ and the phosphate ion, is a 3-. Just a little extra information. These subscripts tell you in this ionic compound what the original charges are, because that's how they're paired. But what else can we say about this? We can say all kinds of things. Just as when I had this definition, 1 inch equals 2.54 centimeters, right? And I said this means it can be written a different way. I'm going to go to black. It means we can write it as a fraction or a ratio. A fraction is a ratio. Like that. Or we can write it the other way. It doesn't matter. As long as your relationship is correct, your numbers are correct, it doesn't matter which order you write it. The order you write it will depend on how you're using it, what you're converting. So I can do the same thing here, right? Erase this. I can make all kinds of statements. I have 3 barium ions per barium phosphate compound, right? I have 2 phosphate ions per compound. I have, for every 3 barium, I have 2 phosphate. Right? For every compound, I have 3 of these and 2 of these. So every 3 of these I find, I'm going to find 2 of these with it. So we can also say that. So we can rewrite these in that ratio. And this is stoichiometry. So we've replaced per with a line, a dividing line. And then we'll rewrite. Here's the first one. I'm going to rewrite it in the format that we use. And we say 3 barium ions per compound. So that relationship can now be used in a conversion. And you can also write it upside down, because the relationship is the same. You can say, I have 1 barium phosphate compound per every 3 barium ions. So in other words, whenever you find 1 barium compound, barium phosphate, you're going to find 3 barium ions. So that's what this relationship says. You can do the same thing with the other 2. So this relationship, we simply write the phosphate ion on top and the compound on the bottom. Or you can reverse it. That's your relationship. And this is per 1 barium phosphate. And this other one, it's the same thing. 3 barium ions. And you're talking about the relationship in this compound. We're not saying in general in the whole wide world. We're saying, given this compound, you can say this about it. We're saying for every 3 barium ions you see, you're going to have 2 phosphates. And you can write this upside down. It's absolutely fine. When you have this, there's no need to reduce these. Let's say this had been a 4 and a 2. You don't need to reduce it down because we're just using it to do math. All right. So that's our stoichiometry. That's the first step in how we use it. But everything goes from this concept, just like conversions all follow the same format. Let's see. So let's go back to slides. So you can see there are some of the examples. Right. And here's another example. They pulled out the phosphorus atoms. So within a phosphate, each phosphate group has one phosphorus, but there are two groups. So there are two phosphorus atoms in this compound. There are 8 oxygen. You have 4 per phosphate group, and you have 2 phosphate groups. So you have 2 times 4. So this subscript has to be multiplied times everything inside the parentheses. So we have 2 phosphorus atoms and 8 oxygen atoms per compound of barium phosphate. So the question we have here says, if I have 21 barium phosphate, say that enough times it sounds funny, formula units, how many phosphorus atoms are there? Well, you start with what you have, 21. Okay, that's an error. It's supposed to say barium phosphate. You can see it was changed here and it wasn't changed here. Pretend this is barium. All right, I'll go to white screen. That's going to confuse you. Sorry. And as many times as I go through these, I don't always catch the errors. So the question was, what do you have? You have 21 barium phosphate formula units. And the question is, how many phosphorus atoms? Okay, so what's our relationship? It's 2 phosphorus atoms, right, for every 1 barium phosphate formula unit. So start with what you have, and what we have is 21 I could write formula units, but I'm limited in space. But as long as what we're canceling out agrees, that's what matters. And just units right now, that will cancel out. It will give what I'm looking for. So now I put numbers in, 1 here and 2 here. So yeah, the question on the slide doesn't match the example. And so your answer would be, I have 42 phosphorus atoms. Okay? So you still treat it the same way you treat any other conversion. The other example on the slide, what the heck? The non-corrected says you have 21 barium ions. And then the question is, how many phosphorus atoms? Well, what's our relationship? Same process. For every 3 barium ions in this compound, I have 2 phosphorus atoms. So every time you have a compound, and every time you have 3 barium ions, you will find 2 phosphorus atoms in that compound. So we start with what we have. I could also just write 2 plus, multiply, put what you're getting rid of on the bottom, put what I want on the top. Okay, this will get rid of that. It gives me what I want. Put my numbers in, make sure you put them in the right order. I'm probably covering that up, but phosphorus is 2, barium is 3. I'm going to flip that, that relationship. And so it's going to be 42 divided by 3, which according to the slide is 14. So any combination of these atoms, ions, etc., units can be used as long as your numbers are correct, your relationships are correct. You can calculate any of these. So that's stoichiometry. And you will be using it throughout your entire chemistry career. So we have this question here. And it says magnesium sulfate and what I'm writing down what I have 28 sulfur atoms. And the question is, how many oxygen atoms? Okay. So let's go back to the whiteboard. So there's our example. So write down what we have. We have 28 sulfur atoms. Put what you want to get rid of on the bottom. Put what you want on the top. Look to see if you have a relationship that you could do this in one step. Well, I have this compound here, and in this compound, for every 1 sulfur, I have 4 oxygen, right? So there we go. So cross out my sulfur. Yep, there's my oxygen. And then 28 times 4, so 80, 32 to 112. Let's see if there's one of those answers on the slide. Oh, good. There is. So the answer is C. And you work it out like any other conversion. Just be careful what you put where. Make sure your units cancel out. Okay. So that's all well and good. But I've been dealing with individual examples, individual molecules, individual formula units, atoms. We don't generally work with individuals, do we? Other than IBM with their carbon monoxide little video, we work with bulk. We work with things that we can go into the lab. We weigh on a scale, grams, milligrams. We measure in milliliters. So how do we use this concept at a scale we actually can use in a regular laboratory? So we have a concept called the mole. Now, on your periodic table, and I actually have one this time. Previous lecture, I was hunting for one frantically. Oh, it will help. All right, so I'll switch over to that in just a minute. On the periodic table, you have the numbers underneath the element symbol. That's the mass, we call that the atomic mass unit, and it's defined. Every unit is defined. This one is defined as 1/12 the mass of a carbon-12 atom, okay? But we don't really go around measuring individual atoms in the general laboratory. So let's look at the periodic table. Hopefully it'll show up. All right. Not great, but you can always pull up yours in your book, print out the one on Canvas. It is there now. All right. Well, anyways, these little blurry things are numbers. Okay. Those are the masses. Notice they're fixed, which means it doesn't change. Every element has a fixed mass. Carbon, this says 12.0107. So that's atomic mass unit if you are talking about a specific individual atom. or in a molecule or in a compound. But it is also, that number works if we talk about something called the mole. So let's meet the mole. And it's a brand new concept. I still remember the first time I was introduced to the mole. I was high school. I will never forget it because it was that strange. And you have to just accept it. This is the one thing about a mole. You have to just accept this definition and start using it. And then after a while, it will fit in your head. It will make more sense. A mole is defined. A mole of anything has a specific number of items. It has 6.022 times 10 to the 23 of them. So, and that is Avogadro's number. So a mole of trees has 6.02, you don't have to use the other two, times 10 to the 23 trees. I don't know how you can fit all of those trees, honestly, in any particular space. A mole of, right, avocados, we have to do that. 6.02 times 10 to the 23 avocados in one mole. That's the definition of a mole. It has a specific number of items in it. A quarter has 25 pennies. It has 5 nickels. These are definitions. Well, a mole has 6.02 times 10 to the 23rd nickels or pennies or quarters, anything that's in there. So when we work with units, when we work with elements, when we work with anything in the lab, we work with them in a state of moles. And the number on the periodic table is for 1 mole of that element, and the unit is grams. So I'm going to come back to that. So we saw this already. This was the exchange. And you can do it with moles. You simply say 6 moles of oxygen atoms, 1 mole of magnesium nitrate. And this is Avogadro's number. And I'm going to go to the whiteboard in a minute. So the molar mass is, instead of taking that number and calling it AMU, we call it grams, and we say it's 1 mole. So let's go back to the whiteboard. So Avogadro's number is defined. It's used to define the mole. It's the count of, so I put brackets here because the bracket is what you're counting. There is your definition of a mole. A mole of anything, a mole of air molecules. A mole of anything has 6.02 times 10 to the 23rd of that thing. And we defined the mass, we call it a molar mass. The other one is just mass, or in AMUs. And when we give a mass in atomic mass units, AMU, that's for the individual. 1 atom, 1 molecule. Molar mass is for 1 mole of anything: calcium, copper, sodium chloride, it doesn't matter. And the number is in grams, and we call it grams per mole. And we usually just do this. So if I go to oxygen and I look on the periodic table under oxygen, I'm going to say, depending on which one you look at, I'm going to see this. If it's 1 oxygen atom, then we say that oxygen single atom weighs 16.00 atomic mass units. But in the lab, when we're weighing out, we say it weighs 16.00 grams per 1 mole. 1 mole of oxygen atoms, 6.02 times 10 to the 23rd oxygen atoms weighs 16 grams. So if you go to the lab and you measure out 16 grams, you weigh out 16 grams of water. You do it by difference. You weigh, tear your beaker, add 16 grams of water, you have a mole of water. You know that because of this definition and the periodic table. So we're going to use that a lot. So the masses on the periodic table we use on a regular basis as grams per mole, because we are saying that number equals the number of grams in 1 mole of that element, molecule, compound, ion, it doesn't matter. And how many of those specific elements, ions, compounds, atoms are there in that 1 mole that weighs that, let's say 16 for oxygen? There are 6.02 times 10 to the 23rd, okay, let's say oxygen atoms in that mole, which weighs 16 grams. You see this circle that we go? And it's extremely useful. The more you use it, you're going to get very good at it. And you're creating new chemistry neurons in your brain. Remember that new language? This is part of the new language. This is vernacular. You're literally creating new chemistry neurons in your brain. And so it takes time for some of this to process, sink in, but you'll get there, I promise you. Oh, all right. So I'll come back to this, but notice this number 3 here. This is molar mass. So I said when you look at the periodic table, there's the molar mass of an element. If you want to know the molar mass of a compound or a molecule, you simply add up each of the elements that make it up, but make sure you use the correct number. All right, I'll go back to that after all. You can always pause this, take a break, come back to it. So, sorry. Let's try that again. Okay, so let's work through a molar mass, because you will need to, this is very possibly going to be a test question, this test, because it's a great simple concept and it's critical. You have to know how to do this. So the slide example says, what is the mass of 1 mole of magnesium nitrate? So what is the molar mass of magnesium nitrate? Okay, it's actually really easy. First, what do you have? You have magnesium 1. Don't worry about whether it's an ion or an element. The difference in size is so insignificant. It's nothing on the scale. It's 24 decimal places back. So for our purposes, they weigh the same. Now, we have 2 nitrate groups. Each nitrate group has 1 nitrogen and 3 oxygens. So make sure you multiply this 2 by what's in the parentheses. So we have 2 nitrogens, and we have 3 times 2, 6 oxygens, all right? That's what makes up 1 individual magnesium nitrate formula unit, or a mole. So we have a mole of all these. So if I look magnesium up on the periodic table, and I'm getting a molar mass, the question was for 1 mole of magnesium nitrate. So I look up magnesium and it's 24 underneath the mg. This is numbers there, 2431. Notice on the periodic table there are no units, because the mass is there for you to use whether it's AMUs or grams per mole, because the mass is going to be the same. I'm going to put my unit at the top of this as a header, as a column, so I don't have to write it every time, but you do have to keep units. So that's magnesium, and so my total magnesium, since I only have 1, is going to be 24.31. Nitrogen, when you look at the periodic table, is 14.01, but I have 2 of them. So the total mass that they contribute to the weight of magnesium nitrate is 28.02. Oxygen is 16 grams per mole. So 1 mole of oxygen weighs 16 grams. but I have 6 of them, so I have to multiply that, and I get 96. I add all these together. We're adding, so we're going to keep our decimal place location. All of these go to the second decimal place, so our answer will be in the second decimal place. And the answer is 148.33 grams per 1 mole of magnesium nitrate. Okay, so you get a molar mass of a molecule or compound by adding up the constituents. Just make sure you don't forget to multiply your subscript outside of parentheses by everything within the parenthesis, or your answer will be wrong. Okay. All right. So we have a question down here. It says, how many oxygen atoms are in 5.45 moles of magnesium nitrate? All right. So let's go back to the whiteboard. I'll just slip this over. So we have a relationship right here, don't we? We have 6 oxygens in a single magnesium nitrate formula unit or a mole. So write down what you have, and according to the slide, I have 5.45 moles. This is a unit. You have to include it. As long as you are talking moles, you can exchange almost anything that has a relationship. Now, get rid of what I don't want and put what I do want. What do I want? I want oxygen atoms. Per mole of magnesium nitrate. I can't get there from here. I have to take an interim step. First, I have to change from magnesium nitrate moles to moles of oxygen atom. You have to go through the mole conversion. Anytime you're changing an identity, the only time you can go number over mole is if your identity is the same. It's not. This is magnesium nitrate and oxygen atoms. Can't do that. So I'm going to actually erase to give myself more room. And let's see if I can work this out without running completely out of board space. So, and if you're just putting units in, it's easy to go back and erase some units and throw some more in. So I have moles. And we're looking for number of oxygen atoms. Okay, so I can't go directly. The first thing I have to do is I have to change my identity. So you're going to change its moles to moles. That's the only way to do this if you're changing identity. We're getting rid of magnesium nitrate. And we're going to moles of oxygen atoms. Just moles of oxygen is fine, because we're not talking about the gas. That's where you start. Now, what's my number? For every 1 mole of magnesium nitrate, I have, you remember, I had 6 moles of oxygen atom. So it's 6 oxygen atoms per individual formula unit, or 6 moles of oxygen atoms per mole of magnesium nitrate. Okay, that will cancel out my magnesium nitrate. Now I have moles of oxygen, right? So I have 2 aspects to my calculation, but now I need to get rid of moles of oxygen and go to number of oxygen atoms. And you can write atoms down here. It's Well, this is Avogadro's number. Anytime you're going to number, that's your final step. And since I have the same identity now, I can do that. And for every 1 mole, I have 6.02 times 10 to the 23rd. My moles, I'm going up here, my moles of oxygen will now cancel out. And I have what I'm looking for. So now multiply 5.45 times 6 times 6.02 times 10 to the 23rd, and you will get your answer. It's just more steps. You just keep putting the units in till they cross out till you get where you're going. If you only put units in first until you get the answer you need, then you go back, put your numbers in. It's easier to not get confused. And then if initially you set something up, oh wait, I can't go directly there, I have to add a couple more steps, it's easy to erase the units and put those more steps in there. I don't have a calculator in front of me to multiply 5.45 times 6 times 6.02 times 10 to the 23rd, but whatever that answer is, it will have 3 sig figs. The relationship with the 6 moles of oxygen per 1 mole of magnesium nitrate is an exact number. It's not used for sig figs. Okay, back to the slides. So this is what 1 mole of each of these items looks like. Notice how much space they take up. Very different. And they look different. We have a liquid. We have a solid metal. We have 2 solid metals. We have a molecule and we have an ionic compound. So this is copper. This is 1 mole of copper. I don't even need to go to the scale to weigh this to see how much it weighs. You go to the periodic table and look up copper. This is the number you're going to see because that definition is that number of grams per 1 mole. And this is 1 mole, therefore it must weigh what it says on the periodic table, the defined mass for copper. So this is 6.02 times 10 to the 23rd copper atoms. And that's what it weighs. This is 1 mole of water molecules. We know what it weighs because we added up the molar mass of 2 H's and 1 O to come up with 18.02 grams for 1 mole of water. And that's what it looks like. This is 1 mole of sodium chloride. There are 6.02 times 10 to the 23rd sodium chloride formula units in here. And since it's an ion, they're all mashed together in crystals. They're not individual. Ionic compounds do not exist as individual formula units. They're always part of a matrix or a crystal or a lattice. And I know what it weighs without having to go through the scale because I add my molar mass of sodium and chlorine together and I get 58.44. Sucrose is a fairly large molecule compared to the others, and sure enough, look at how much space it takes up. Granted, there's air in there, but still, there's air in here too. So if I add up all the carbons and all the hydrogens and all the oxygens in sucrose, 1 molecule, I will get 342.3 grams, and that's what this weighs for 1 mole. And then here is 1 mole of aluminum. And there are 6.02 times 10 to the 23rd aluminum atoms in this ball of foil, and it weighs 26.98. So each of those is a mole. We know what it weighs by the definition. And by using moles of something, we can actually measure them at in a standard scale. And then of course, this is what a mole looks like written out. That's a lot of zeros. I mean, there's, how this has million, billion. Okay, my numbers actually got shifted. They're supposed to be over right. So this is the million, that's the billion, that's the trillion. No, that's 100,000. All right. See, I get confused. This is correct. But that's a lot of zeros. And then that's how many individual molecules or atoms or formula units were in those previous examples. exactly. Give or take a few on this end. So that's why another reason why we use scientific notation. So we don't have to write all those zeros. So just to recap, an atomic mass unit is an individual molecule or element, ion, atom, compound. That same number can be used in the lab, and we apply it to 1 mole of the item, and we say it weighs that number of grams. Let me do something. Whoops. Okay. So I worked this out in the lecture, so I won't do it again here, and it's done right here for you. You have a number of something, so a number means you're going to use Avogadro's number relationship. Mole is an amount. So you start with what you have. You cross out, in this case, it's ions, is what your thing is. And you say, I want to mole, so you cross out what you don't want, which is ions, and you make the relationship for moles using Avogadro's number, and you can get the number of sodium ions, this number of sodium ions in moles. If you have moles of something and you want to change it to how many units, how many particles, how many pieces, how many ions, how many atoms, if that's the question you're asked, you're using Avogadro's number. Start with what you're given. We're given 3.24 moles of sodium chloride. Put what you want to get rid of on the bottom because it's the opposite side, and put what you want on the top, which is the individual units. Using Avogadro's number, cross out your moles, and that's how many individual formula units you have in 3.24 moles of sodium chloride. Okay. So let's go to the whiteboard. So the question on the slide is 0.0078 moles of sodium ions. And the question is, how many? What number? Number, you see number, you know Avogadro's number is going to be used. So once again, start with what you have. Remember Avogadro's number, I did this, and I put brackets. So in this case, ions are going to go in your bracket, sodium ions. But we're going from an amount of it, a batch, to individual numbers. So we start with what we have. And I'm going to run out of room. So you're getting rid of moles, and you're just adding a number. And I'm not sure how to, this just with practice, you'll get used to using this. But my relationship is for every 1 mole of sodium ion, I have this many individual ions. So I can cancel out that, and that's going to be the math that I do. guess I should get a regular old calculator here. So 0.0078 times 6.02. All right. Told you, new phone. I have to set it up as a scientific calculator. Let's just go to the one on the code. 0.0078 times 6.02. And my calculator here has an EXP key to put in the 23. And then it gave me the number in regular notation with all those zeros. So I have an F-E button. I click and it gives me the number in scientific notation. And it says it's 6,956 times 10 to the 21 ions. I have, how many sig figs do I have here? These are placeholders. I have 2 sig figs, which means I only want those 2 digits. So I'm going to say 4.7 times 21 ions. And let's go back to the slide. And there it is. So the answer is B. So working these two out, I think you can start to see that with practice, there is a certain amount of repetition. There is a certain amount of sameness that you're doing with these exercises, and you will create, muscle memory. Especially if you always start the same way. It helps warm your brain up. Write down what you have and what you're looking for as your focus point. And then start with what you have. And then go from there with units. If you do that the same way, it helps warm up your brain. You're sometimes just not sure what we're doing. So this question is the mass of, so that's my question, 4.25 moles of H2O. So here's what I'm given and here's what I'm being asked for. So what's the first thing you do? You put down what you have. I have 4.25 moles of water. Okay, draw your line. What am I getting rid of? I'm getting rid of moles. Because I am not changing the identity, I'm just going to put water right here because it's the same top and bottom. What do I want? I want mass. Mass is grams. Anytime you see mass, it's asking you for grams. Well, what's my definition for water? If I go to the periodic table, hydrogen has 1.008 or 1.01, depending on what number you use. Oxygen is 16. I have 2 hydrogens. So my water weighs this. Grams per mole. It's not grams, it's grams per mole. You have to have a whole mole of it for it to weigh 18.02 grams. So I will be able to get rid of my moles and get grams. That's what I asked for. So now I can put my numbers in. For every 1 mole of water, I have 18.02 grams. And then according to the slide, you get, your calculator will spit out 76.585 grams. You go back. I have 4 sig figs here. I have 3 here. I'm multiplying. So I want 3 sig figs. So my answer will be 76.6, I'm going to round up, grams H2O. Okay? The other question on that same slide, said, how many moles of water is 4.25 grams? So before we went from moles to grams, now we're going from grams to moles. So the question is, how many moles, and what do we have? We have 4.25 grams. So pretend that's written up here. Again, put down what you have. Draw your line. What am I getting rid of? This time I'm getting rid of grams and I want moles. And I'm just going to put water in the halfway point because it's the same top and bottom. Water is still 18.02. It will forever be 18.02 grams per mole. Very few things you can say always or never about in chemistry. That's one you can say always about. So by that definition, and yes, this will get rid of my grams and give me moles. I have 1 mole for every 18.02. So make sure you don't write this backwards. I'm very guilty of this. I will almost always put my grams on top, my mole on the bottom. And I only catch myself because I check my units to see if they cancel out. So check your units to make sure you didn't make that mistake. It's very easy to do. So now I'm going to divide 4.25 by 18.02, and I get 2.36 moles. 3 sig figs here, 4 here. My answer is in 3 sig figs. So that's correct. The next slide, it asks, what is the molar mass of magnesium sulfate? Now, previously, I did magnesium nitrate. So this actually will be easier because we don't have a parenthesis to deal with. So what do I have? I have 1 magnesium. I have magnesium, sulfur, and oxygen. I have 1 sulfur, and I have 4 oxygens. So I go to my periodic table, which I know is fuzzy, and I'm going to go to magnesium, and I'm going to get that little number down there, and you're going to get it from your periodic table, and it says 24.305 grams, and I'm just going to head it here. These are all grams per mole. Sulfur is 32.065. And oxygen is 60.00. I have 4 of them, so I have to multiply that times 4. So that's going to be 64, 32, and 24. Now notice I only have 2 decimal places here. I have 3 here. So my answer, I'm going to bring the whole answer down, but my final answer can only go to the 2nd decimal place, because I didn't include anything in the 3rd. So I can use my phone for this one. So I said 24.305, 32.065, and 64. And I end up with 120.37, and if you were doing this by hand, you would bring that one down too. But you're only going to give your answer to that decimal place. And what is my unit? So your answer is this, grams per mole. Do not forget your units or your identity. If you just give me a number, it's useless. Every number must have a unit for it to have meaning. And so when we go back to the slide, and this is slide 17, the answer is C, 120.37. You'll see that. It's iClicker question 3. Okay. The next slide, iClicker question 4, says, so I'm going to go back and write down, my answer was 120.37 grams per mole for magnesium sulfate, because I'm going to need that number. So the next question says, I have, what do I have? I have 401 grams. And the question is, how many moles? Now, normally, if you say how many, you want to think Avogadro's number. But if it says how many moles, moles is your other definition. So, same way every time, put down what you want to get rid of. We have not changed identity, so I'm just going to write the identity to the side in between the two. I can do that in one step. Yes, my grams will cancel out, so I didn't write it upside down. Now I can put my numbers in. For every 1 mole, because I figured it out last slide, I have 100, 120, 37. And when I do my math, oh, there's my scientific calculator. Aren't new phones fun? 401 divided by 120.37. And I get 3.3314 moles. Now, this is 5 sig figs. This is 4 sig figs. I'm dividing, therefore I have to, I'm sorry, this is 3 sig figs. It has a 4 in it. 3 sig figs and 5, so my answer has got to be in 3. And so I'm just going to erase the other two because they're, so my answer is 3.33, and in the slide that would be answer A. Actually, we can go back to that now. So this one, the answer was C, 120.37. And then we just worked this one out, and it was A, 3.33 moles. So again, this is that flow chart of your, if you notice whether you're going to mass or you're going to number of items, you have to go through mole. And particularly if you are converting identities, if you are converting species, magnesium sulfate to the oxygen, you have to go through moles. You cannot directly convert those gram to gram. You have to go through moles. It's the only way to do it. Any other way will be wrong. So everything goes through moles. So you convert to mole, convert to your answer, or change the identity and go back to grams of the other species. And then here's a horizontal version of the same flow. Going from mass to number of moles or moles, you use gram per mole. Number of molecules or atoms. So this is using an example of atoms within the molecule. So it's saying, okay, number of molecules in the mole of that molecule, and then number of atoms within the molecule. But just make sure you put it in the right order so they cross out correctly. Okay. So I'm just checking the time, so I have to go in a minute. All right. So we'll start with the top one. I do recommend these two. They're good examples. Work them out on your own. Write down the question on a separate piece of paper, work it out, see if you can get it. These are really good examples without looking at how it was done. So what do we have? We have 4.25 grams of H2O, of water, and the question is number of oxygen atoms. Okay. Notice we're changing species, we're changing identity. So at some point you have to go through moles of water, moles of oxygen exchange. They have to be in moles. You cannot do it any other way. Oh, it might help if I share the whiteboard. Okay. So anytime you are changing species, you have got to have a mole to mole switch. So what are we starting with? all right? The first thing you do is change to moles. And I always say, when you get an equation, a problem, a question, you're not sure what to do because we're going to get more complicated, so change something to moles. Just do it. 90% of the time, that's going to put you in the right direction. Warms up your brain, and it helps you get a handle on, oh, right, now I know how to solve this. So when in doubt, change something to moles. 90% of the time, you're going to be right. So we're still doing water because I am going to change species. I'm going to keep it. And so first I'm going to write my units. So this will cross out my grams. Now I'm in moles of water. Okay, now I'm on the Molar Express. I can swap identities. I can swap anything as long as the relationship is true. So I'm going to swap identities. I'm going to swap my moles of water. I always pictured this as like a car with carrying moles, with my moles of oxygen. Okay, that will get rid of my moles. Now I have moles of oxygen. Great. But it's asking for the number of oxygen atoms. Number means Avogadro's number. So continue down here. Make sure another reason to do it, you can do it all in one stretch. I have moles of oxygen on top, so I have to get rid of it on the bottom. And my number of oxygen atoms. Okay, that's going to cancel that out. All right, all of my units canceled. I have what I'm looking for. Let's put numbers in. My relationship, grams per mole for every 1 mole, they're 18.02 grams of water. What about this one? For every 1 mole of water, we have one mole of oxygen, right? We have 2 moles of hydrogen and 1 mole of oxygen. And for every 1 mole of oxygen, we have how many oxygen atoms are in a mole of oxygen? Avogadro's number, 6.02 times 10 to the 23rd. All right. Now you just plug and play. 4.25 times 6.02 times 10 to the 23rd equals, hit equals on your calculator, and I say divided by 18.02 equals. That's how you do it in one step. Do not stop and write things down in the interim. That's a way to make mistakes, drop numbers, put them back in wrong when you put them back in the calculator. So do it in one long step. So you're going to multiply 4.25 times 6.02 times 10 to the 23rd. You're going to say equals. Then you're going to divide by 18.02. And on the slide, it gives the answer of 1.42 times 10 to the 23rd oxygen atoms. We have 3 sig figs there. We have 4 sig figs there. That's an exact number. That's a defined, so it's an exact number. So we would use the 3 sig figs. And in fact, it's in 3 sig figs. Okay, last one. Second one on this slide says, question is how many barium ions? So that's a specific particle, right? How many ions? So that's Avogadro's number. And what do we have? We have 4.25, and I'm just going to go ahead and write it here, grams of this compound. We met him at the very beginning of the lecture. All right. So first thing, convert to moles. Because it's just a good thing to do, and you're going to need to do it because we have to have moles to convert anything. I am changing identity. I am changing identity from a compound to an ion. So I'm going to write my compound here, even though it's kind of a pain. It's better than making a mistake. All right. So now we have moles of the compound. Good. Now that we have moles of the compound, we can exchange identity. So I have moles of my compound, and I want moles of barium ion. Okay. My moles of compound will cancel, and now I'm in moles of barium ion. But it's asking us for the number. Well, that's Avogadro's number. So you put your moles, and here you can, we're at the end point, so you can put the barium on the side. And then this is, well, I'll say ions as a placeholder. So this will cancel out my moles of barium, and it'll give us individual ions. I'll say number as my placeholder. All right, now let's put some numbers in. So this units all cancel out. It gets me where I want to go. So barium phosphate, and I'm just going to use the slide. If you add up all of those atoms in there, in fact, I would recommend that you go practice this and make sure you can come up with the correct molar mass of barium phosphate. That's a good one to practice because it's so big. And you end up with 601.92. And then over here, for every 1 mole of barium phosphate, how many barium ions do I have? I have 3, right? There's that subscript. That's what it tells me. So that goes here. And then for every 1 mole of barium ions, there, I have Avogadro's number. Now I'm going to say 4.25 times 3 times 6.02 times 10 to the 23rd equals, in your calculator, divided by 601.92 equals, and that's going to give you your number. And on the slide, it gives us 1.28 times 10 to the 22 barium ions. It says atoms, but it's ions. Same difference. 3 sig figs, 5 sig figs. So we're multiplying and dividing. We're going to count. You go with this lowest number, and that's 3. So it's 3 sig figs. I know, it's a mess, isn't it? But it's correct. Everything cancels out. So there you are. Like I said, I highly recommend you practice these. Go in also and calculate the molar mass from barium phosphate on your own, and then see if you got it right. It's a great exercise. All right, that's the end of part 1. The second part of the lecture, lecture 6, is going to be the percent composition all the way to molecular formula. Okay.